The purpose of the experiment was to demonstrate how stray electrical currents can accelerate corrosion and ultimately cause the failure of a metallic pressure vessel. A controlled setup was constructed to replicate the conditions found in a submerged steel pipeline. The capsule used in the experiment was connected to a regulated electrical circuit that discharged ions into the experimental electrolyte. All measurements, including voltage, current and pressure, were recorded digitally with time-stamped data and supported by continuous video documentation. During the course of the experiment, corrosion developed at the points of anodic discharge in exact accordance with Faraday's laws of electrolysis. The metal loss was both measurable and progressive, reducing the wall thickness of the capsule over time. This weakening directly affected the vessel's ability to contain internal pressure, clearly demonstrating the destructive impact of accelerated corrosion under the influence of stray current electricity. As the test continued, the internal pressure eventually exceeded the structural strength of the remaining wall thickness. The vessel ruptured violently, reducing gas in a burst that visually and acoustically resembled an explosion. Importantly, no external detonation or mechanical impact occurred. The rupture was purely the result of internal pressure acting on a corroded and structurally compromised section of metal. All experimental data was logged and verified through automatic digital systems, ensuring complete integrity and reproducibility. Photographs and video recordings documented each stage, from the initial setup through corrosion progression to the final rupture event. The recorded measurements confirmed the theoretical relationship between electrical current discharge and metal dissolution. This experiment conclusively demonstrates that stray current-induced corrosion is capable of producing catastrophic pipeline failure under operational conditions. When sacrificial anodes become depleted, or when stray electrical currents of higher potential enter the system, the pipeline steel becomes anodic and begins to dissolve. Once sufficient metal is lost, even normal operating pressures can exceed the hoop stress. Weakened metal yield strength, causing rupture. The resulting rapid gas release produces the same physical effects as an explosion, though its origin is electrochemical and mechanical rather than explosive. The implications for subsea pipelines, such as those in the Nord Stream system, are clear. Stray electrical energy potential differences between structures and interference from nearby systems can accelerate corrosion far beyond expected design limits. When combined with pressure variations during operations such as pigging, these factors can trigger failure at the weakest points, typically where anodes have been depleted or coating faults exist. This proof of concept has been experimentally verified. The results are observable, measurable and repeatable, providing a scientifically sound explanation for internal pipeline failure caused by accelerated corrosion. The expertise required to conduct such investigations and experiments can only be obtained by studying cathodic protection network science and technology, which are available through our training courses.